In this video, we're going to be looking at problem number 3 from the practice problem sheet for lesson 2 from module 5. We're going to be using Simpsons rules to look at the situation where we have a vessel with an appendage and we have to use intermediate ordinates. So our first step will be to calculate h, the common interval, which is the width between each of the semi-ordinates. And note that the width of the appendage is also h. Our total length of the vessel we've been given is 90 meters. And we have nine area segments. 1, 2, 3, 4, 5, 6, 7, 8, and the appendage counts as our ninth. So 90 divided by 9 gives an h value of 10 meters. So let's look at the appendage of the vessel first. That's this section here. It has three semi-ordinates, 6.4 and 0.4, and then the intermediate semi-ordinate 5.5, which is exactly halfway between the two end semi-ordinates. Because there are three semi-ordinates, we can use Simpsons' first rule. It looks like this. And that requires an h value and a value for the area function. Now when we calculate an area function, if you recall, we need to know the multipliers for the rule, and because we have we're using Simpsons' first rule, the 1, 4, 1 will be our multipliers. And because the width of the interval, there's two intervals or two area segments, because the width of those is half h, then we can divide our h value by 2 and multiply by the area function. We could also, though, instead of dividing the interval, the common interval, by 2, we could divide the area function by 2. It wouldn't change our answer, but what it will do is give us an advantage in later calculations, because we'll be able to use the same h value for both the appendage and the remainder of the waterplane area. And having that common h value will be helpful, as we'll see later on. So when we divide the area function by 2, that has the effect of having our multipliers. So instead of 1, we'll have 0.5, 2, and 0.5 as our Simpsons' first rule multipliers for the appendage. Okay, so we've got our multipliers for the appendage. We're going to be using Simpsons' first rule, and these will be our multipliers for the appendage. And we now need the multipliers for the remainder of the vessel. So if we look at the rest of the waterplane area, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 semi-ordinates. Again, that means we can use the first rule, and its multipliers will follow the pattern 1, 4, 2, 4, 2, 4, 2, 4, 1. Now, what's interesting is that if we look at the semi-ordinate 6.4, it has a multiplier of 0.5 for the appendage calculation and a multiplier of 1 for the remainder of the waterplane area. So because I'm going to use a common h value in my calculations for both the appendage and the remainder of the vessel's waterplane area, then I can add 0.5 and 1 and give that semi-ordinate 6.4 a multiplier value of 1.5. So my multiplier values for the whole calculation are going to look like this. 0.5 plus 1, 1.5, then 2, then 0.5. So I can use these multipliers in my table of values with my common H value to calculate the water plane area of the vessel with its appendage. So now we'll use our table of values to organize our individual area function calculations. That's the half ordinate multiplied times its Simpsons rule multiplier gives an individual area function, and then we sum the individual area functions up to get a total area function for our water plane area calculation. We're going to use these multipliers, which follow the usual sequence except for the 3 semi-ordinates in the appendage. So writing down the half ordinate values then, 0, 3.7, 6, 7, 8.1, 8.4, 8, 7.1, 6.4, 5.5, and 0.4, followed by the Simpsons rule multipliers for this example. Now multiplying across in each row, 1 times 0 is 0, 3.7 times 4 gives us 14.8, and so on. And 0.2. Then summing up the individual area functions, we get a total area function of 169.8. Using Simpsons rule, Simpsons first rule then, the area will be 1/3 times h times our area function, which is 1/3 times 10 times 169.8, and then I'm going to multiply by 2, because we recall that we want the entire water plane area, not just this first half. So we use Simpsons first rule to get the first half of the water plane area, then double it to get the total water plane area. So our final answer is 1,132 meters squared.